Download this code from codegive.com, link in the description below. OK, let's dive deep into the world of vacuuming, not the chore kind, but the fascinating reinforcement learning technique called temporal difference, TD, learning with a gridworld vacuum cleaner example. We'll cover the theory, implementation in Python, and explore variations. Get ready for a thorough journey. Introduction: what is TD learning and why a vacuum cleaner? Reinforcement learning, RL, in a nutshell. RL is about training an agent to make decisions in an environment to maximize a reward. The agent learns by trial and error, receiving feedback in the form of rewards or penalties for its actions. Think of it like training a dog: you give it treats for good behavior and correct it for bad behavior. Temporal difference, TD, learning. TD learning is a specific type of RL algorithm. What sets it apart from other methods like Monte Carlo, MC, methods is that it can learn from incomplete episodes. MC methods have to wait until the end of an episode to update their value estimates. TD learning can update after each step. This makes TD learning more efficient in many situations. The gridworld vacuum cleaner analogy. Imagine a simple gridworld environment. A vacuum cleaner robot lives within this grid. Its goal is to navigate the grid and clean up dirt, represented by specific states. The agent receives a reward for cleaning dirt and may incur a small penalty for each step it takes, discouraging wandering aimlessly. This is a classic and intuitive example to illustrate the concepts of TD learning. 2. Core concepts: states, actions, rewards, policies, and value functions. Before we dive into the code, let's solidify the key concepts. 1. State, a representation of the agent's current situation in the environment. In our vacuum cleaner example, the state could be the robot's x, y coordinates on the grid and a boolean indicating whether there is dirt at that location. 2. Action, a choice the agent can make at each state. For the vacuum cleaner, this might be up, down, left, right, suck, to clean if dirt is present. 3. Reward, a numerical value that the agent receives after taking an action. This feedback signals whether the action was good or bad. Example: *+10 for sucking dirt. *-1 for moving to a new empty location. *-10 for bumping into a wall. 4. Policy, is strategy that tells the agent which action to take in each state. A policy can be deterministic, always take the same action in a given state, or stochastic, take different actions with certain probabilities. 5. Value function, VS, an estimate of the expected cumulative reward that the agent will receive starting from a given state S and following a specific policy pi. It answers the question: how good is it to be in this state? The goal of TD learning is to accurately estimate this value function. 6. Q value function, Q, S, A, an estimate of the expected cumulative reward that the agent will receive starting from a given state S, taking action A, and then following a specific policy pi. It answers the question: how good is it to take this action in this state? 7. Discount factor, gamma, a value between 0 and 1, typically close to 1, that determines how much the agent cares about future rewards. A discount factor of 0 means the agent only cares about immediate rewards. A discount factor of 1 means the agent cares equally about all future rewards. It's useful to prevent infinite sums and also to express a preference for rewards sooner rather than later. 3. Temporal difference, TD, learning, the algorithm. TD learning updates value estimates based on the difference between the current estimate and a sample of the actual reward plus the discounted value of the next state. This is the key equation, where asterisk v, s, the estimated value of the current state s, asterisk alpha, alpha the learning rate. A small value, example 0.1, means the updates are small and gradual. A larger value, example 0.9, means the updates are more drastic. Asterisk r, the reward received after taking an action in state S. Asterisk gamma, gamma the discount factor. Asterisk v, s, the estimated value of the next state S, the state the agent transitions to after taking the action. Asterisk r plus gamma asterisk v, s, v, s, this is the TD error. It represents the difference between what the agent expected to happen and what actually happened. 4. Code example, a simple TD, 0, implementation, Python. Let's build a basic grid world environment and implement TD, 0, learning. TD, 0, is the simplest form of TD learning, updating based on just one step of experience. Explanation asterisk. 1 Grid world class asterisk. This class defines the environment. It handles the grid, agent position, dirt locations, and the rules for taking actions. The step, method is crucial. It takes an action, updates the environment state, and returns the reward, the next state, and a boolean indicating whether the episode is done, all dirt cleaned. 2 TD agent class asterisk. Asterisk underscore underscore init underscore underscore, initializes the agent with the environment, learning rate, alpha, discount factor, gamma, and a value underscore table, a number pi array, to store the estimated value of each state. The value underscore table is initialized to zeros. Asterisk choose underscore action, implements a simple epsilon greedy policy. With a small probability, epsilon, the agent takes a random action, exploration. Otherwise, it chooses the action that leads to the state with the highest estimated value, exploitation. Asterisk test underscore action, this is a helper function. It does not change the actual environment, but we use it to predict the next state of our agent to find the optimal action. Asterisk learn, implements the TD, 0, update rule. It calculates the TD error and updates the value of the current state in the value underscore table. 3 training loop asterisk. This is where the agent interacts with the environment and learns. For each episode, asterisk the environment is reset. Asterisk the agent takes actions according to its policy. Asterisk the agent receives a reward and observes the next state. Asterisk the agent updates its value function using the TD, 0, update rule. Asterisk this continues until the episode is finished, all dirt cleaned, or a maximum number of steps is reached. For evaluation asterisk after training, we print the learned value function. Ideally, states closer to dirt locations should have higher values. V enhancements and variations. This is just a starting point. Here are some ways to improve and extend this example. 1 Epsilon greedy policy improvement asterisk. Asterisk epsilon decay asterisk. Start with a higher epsilon, more exploration, and gradually decrease it over time, more exploitation. This helps the agent find a good initial policy and then refine it. Example. You'll also need to modify your choose underscore action method to accept epsilon as an argument. 2 Q learning asterisk. Instead of learning the value function v, s, learn the q value function q, s, a. Q learning is an off-policy TD learning algorithm, which means that the policy used to choose actions, the behavior policy, can be different from the policy being evaluated, the target policy, which is typically a greedy policy. The update rule is Implement a q_table and update it in the learn method. Your choose_action method will need to select actions based on the q values. 3 Sursa*Sursa is an on-policy TD learning algorithm. This means that the policy used to choose actions is the same policy that is being evaluated and improved. The update rule is: the key difference from Q learning is that you use the Q value of the actual next action, A, taken by the agent, not the maximum Q value. You'll need to select the next action before updating the Q value. For eligibility traces, TD, lambda, TD, lambda, is a generalization of TD, 0, that allows the agent to update the values of all states visited in an episode, not just the immediately preceding state. This is done using an eligibility trace, which is a temporary memory of which states have been visited recently. This can significantly speed up learning. 5 more complex environments ***. Add obstacles to the grid world. ** introduce different types of dirt, example some are harder to clean. * give the agent a limited battery life. 6 Function approximation * for large state spaces, it's often impossible to store the value function or q-value function in a table. In these cases, you can use a function approximator, such as a neural network, to estimate the value function. 7 Visualization * use libraries like Matplotlib or Seaborn to visualize the agent's learning progress and the learned value function or q-value function. 6. Key considerations. * learning rate, alpha a crucial parameter. Too high, and the learning will be unstable. Too low, and it will learn very slowly. Experiment to find a good value. Often, decaying the learning rate over time is beneficial. * exploration exploitation trade-off * the agent needs to explore the environment to discover new and potentially better actions, but it also needs to exploit its current knowledge to maximize its rewards. Balancing these two is essential. Convergence TD learning is guaranteed to converge to the optimal value function under certain conditions, example a decaying learning rate, exploration of all state action pairs. However, in practice, it may take a long time to converge, especially for complex environments. 7. Conclusion. This tutorial provides a comprehensive introduction to TD learning with a practical vacuum cleaner grid world example. By understanding the core concepts, experimenting with different algorithms and variations, and carefully tuning the parameters, you can apply TD learning to solve a wide range of reinforcement learning problems. Good luck cleaning up the world.